Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. What we are going to look at in this module is how to extract multipath diversity in a CDMA system. That is, we are concerned with a new form of diversity that is termed as multipath diversity in the CDMA system, and this is possible through what is known as the rake receiver. This is the rake, R-A-K-E, the rake receiver for our CDMA or code division multiple access systems. So, to illustrate this concept of multipath diversity, let us consider a frequency selective channel. We have not considered, we have only considered a flat fading channel so far. Let us now consider a frequency selective channel. Let us see how a frequency selective channel can be modeled in a wireless communication system. So, let us look at a frequency selective we have our frequency selective channel. So, for this frequency selective channel, consider the transmission of symbols x0, x1 up to xn, then the output yn is given as yn is equal to h0 times xn plus h1 times xn minus 1 plus h2 times xn minus 2 plus so on hl minus 1 times x n minus l plus 1 plus wn. So, what we are seeing is that yn is equal to h0 times xn plus h1 times xn minus 1, so on so forth until hl minus 1 times xn minus l plus 1 plus the noise. So, we are seeing something very interesting. We are seeing that the output symbol yn depends not only on the current input symbol xn, but it also depends on the past input symbols, namely xn minus 1, xn minus 2, so on until xn minus l plus 1. Therefore, this is precisely inter-symbol interference. This system model, you can clearly see in this system model, we have inter ISI or inter symbol interference. This can be succinctly represented in the summation form as yn equals summation L equal to 0 to capital L minus 1 h of L x of n minus L plus w of L, and we are saying that this summation of xn which depends on xn, xn minus 1 onto xn minus L plus 1, this represents inter symbol inter-symbol interference, or basically ISI, right. So, this represents inter-symbol interference, correct, because the output yn depends not only on xn, but also on the pass symbols. So, the pass symbols xn minus 1, xn minus 2, so on are interfering with the current symbol, that is xn. Therefore, this represents inter-symbol interference. And previously you might remember that we said inter-symbol interference is basically arises from a frequency selective channel. We have said that inter-symbol interference in the time domain is the same thing as frequency selective fading when looked at in the frequency domain. So, this inter-symbol interference channel represents nothing but a frequency selective fading channel. So, therefore, this ISI channel is basically the model for a frequency selective this is the model for a frequency selective fading channel. Since frequency selective fading in the frequency domain, right, where the bandwidth of the signal, remember, is greater than the coherence bandwidth of the channel, this leads to frequency selective fading in the frequency domain, which basically implies inter-symbol interference in the time domain. So, therefore, this is a model for frequency selective fading. Now, let us look at a CDMA transmission or the corresponding symbols that are transmitted in a CDMA system. We know that in a CDMA system, the transmitted symbol xn is given as the symbol A0 multiplied by the code C0 of n. So, for CDMA system, we have x of n equals A0 times C0 of n, that is the product of the symbol times the code sequence. Now, let us substitute this xn in the frequency selective system model above, and we will receive yn is equal to summation L is equal to 0 to L minus 1 HL A0 times C0 n minus L plus W of n. Okay. So, substituting xn is equal to A0 C0 n or xn minus L equals A0 C0 n minus L, we get this equivalent system model. Now, at the receiver we correlate yn. So, this is the yn that is received in this CDMA system across the frequency selective channel. At the receiver we will correlate this yn with the code sequence C0 n, because at the receiver in a CDMA system we correlate with the spreading sequence or the chip sequence of the particular user. Therefore, at the receiver we perform the correlation operation. At the receiver correlating with code C0 of n, we have 1 over n summation n equal to 0 to n minus 1 yn C0 n equals 1 over n. On the right hand side we have summation which is equal to summation 1 over n summation n equal to 0 to n minus 1 summation L equal to 0 to L minus 1 HL A0 C0 n minus L C0 n plus 1 over n summation n equal to 0 to n minus 1 W n C0 of n. And we have already seen this 1 over n summation W n C0 of n, this is noise W tilde which is Gaussian with mean 0 and variance equal to sigma square divided by n. So, this 1 over n summation W n C0 n, this is Gaussian noise with mean 0, variance sigma square divided by n. This we have already seen. Now, let us rewrite the signal part so that we gain some insights into this. So, the signal part can be written as, so now if I denote this quantity by R0, if I denote this correlation by R0, I can write the signal part as R0 is equal to 1 over n summation L equal to 0 L minus 1 HL A naught, also take the 1 over n inside, 1 over n summation n equal to 0 to n minus 1 C naught n minus L C naught n plus our noise component W tilde. Now, if you look at this correlation component 1 over n summation over n C naught n minus L to C naught n minus L times C naught n. Now, this is nothing but the correlation, the shifted correlation, this is nothing but the autocorrelation of code. This is the autocorrelation of the code C naught of n, and we have already seen the autocorrelation properties of the PN sequences. This is equal to, this autocorrelation is equal to 1 if L is equal to 0, and this is equal to minus 1 over n, which is approximately equal to 0 if L is not equal to 0. So, we have seen that this product 1 over n summation over n C naught n minus L times C naught n, this is the autocorrelation of the code sequence C naught n. This is equal to 1 if the shift L is equal to 0, and it is approximate, it is equal to minus 1 over n, which is approximately equal to 0 for large n if L is not equal to 0. Therefore, I can approximate R of 0. So, I can ignore this correlation if L is not equal to 0, which means I can only retain the term corresponding to L is equal to 0 in this summation to basically derive the expression for R of 0 as R of 0 is equal to H of 0 times A naught of 0 plus W tilde, where we have ignored in this signal component, we have ignored terms corresponding to L not equal to 0, since autocorrelation equals minus 1 by n, which is approximately equal to 0. Since we ignored these terms which correspond to L not equal to 0. Therefore, R of 0, that is correlation with C naught of n, can be expressed as H of 0 times A naught plus W tilde, where W tilde is again the Gaussian noise with mean 0, variance sigma square divided by n. Now, let us look at something slightly different. Let us look at correlation with a delayed version of the chip sequence. Let us look at correlation of Yn with C naught n minus 1. So, let us look at the correlation of Yn, correlate Yn with C naught n minus 1, that is delayed the delayed version of the code, because C naught n minus n naught is a delayed version of the code C naught, and here n naught is equal to 1, and this correlation can be expressed as 1 over n summation n equal to 0 to n minus 1 Yn C naught of n minus 1, which is equal to 1 over n summation L is equal to 0 to L minus 1 H of L A naught, I will take the 1 over n factor inside, this will be 1 over n summation n equal to 0 to n naught C naught n minus L C naught n minus 1 plus 1 over n summation n equal to 0 to n minus 1 W n C naught n minus 1. Now, let me call this as R1, this correlation with C naught n minus 1 as R1. Now, again this noise which is 1 over n summation W n C naught n minus 1, I can denote this by W tilde 1, which will be again Gaussian noise with mean 0, variance sigma square by n. Now, if you look at this inner summation, that is summation 1 over n C naught n minus L into C naught n minus 1, this is the autocorrelation of the shifted sequence C naught n minus 1, right. Therefore, this will be equal to 1 if the shift between these two sequences is 0, that is L is equal to 1, and this is equal to minus 1 over n if L is not equal to 1 or approximately 0 if L is not equal to 1. Therefore, if we examine this inner autocorrelation, the inner autocorrelation is 1 over n summation over n C naught n minus L C naught n minus 1, which is equal to 1 if n is equal to, if L is equal to 1, if the shift L is equal to 1 is equal to minus 1 over n, which is approximately equal to 0 if L is not equal to 1. Therefore, when you look at this inner summation, only the term corresponding to L equal to 1 will survive, and therefore, again I have R of 1 is interestingly, that is H of 1 into A naught plus W tilde of 1, because only term corresponding to L equal to 1, only the term corresponding to L equal to 1 will survive after this correlation with the shifted sequence C naught n minus 1. Similarly, one can correlate with C naught n minus 2, that is shifted by 2 chips, C naught n minus 3, so on and so forth, C naught n minus L plus 1. Similarly, one can correlate C naught n minus 2, C naught n minus 3, so on, C naught n minus L plus 1. The corresponding outputs can be expressed as, after correlation with these various shifted versions of the code sequence C naught, the corresponding outputs can be expressed as well, we have R0 equals H0 times A naught plus W tilde 0, R1 corresponding to correlation with C naught n minus 1 equals H1 A naught plus W tilde 1, so on and so forth. We have R L minus 1 equals h of L minus 1 A naught plus W tilde of L minus 1. Now, I can write these as a vector. These various outputs obtained by correlation with the various shifts of the code sequence C naught n, I can write this as a vector. Therefore, I have R bar is equal to H bar times A naught plus W bar, where each element of W bar is Gaussian noise with mean 0 and variance sigma square. Each element therefore, I have my model is equal to R bar equals H bar A naught plus W bar. And if you look at this model, this model is very similar, in fact exactly identical to the model of the multiple antenna wireless communication system, where the different channel coefficients across the antennas are H0, H1 up to HL minus 1. We had an exactly similar model, that is R bar or Y bar equals H bar x plus W bar. Here we have R bar, that is these different statistics at the output of the correlator. What are these statistics? These statistics correspond to correlation with different shifted versions of the code sequence C naught n. So, R0 corresponds to correlation with C naught n, R1 corresponds to correlation with C naught n minus 1, so on. RL minus 1 corresponds to correlation with C naught n minus L plus 1, which is equal to H bar, the channel, which H bar is the vector of channel coefficients. H bar, the vector, contains the coefficients H of 0, H of 1, H of L minus 1. These are the coefficients. These are the coefficients of the frequency selective channel. These are also known as the taps of the frequency selective channel. These are the coefficients. These are the coefficients also known as the taps. These are known as the taps of the taps of the frequency selective channel, and the noise vector W bar is such that each element is Gaussian with mean 0 and variance sigma square divided by n. And now therefore, the optimal processing is once again similar to that of the multiple antenna wireless communication system. The optimal processing is through the maximal ratio combiner. So, the optimal processing now is to use maximal ratio combiner on R bar equals maximal ratio combining, that is MRC on R bar, which is basically equal to H bar Hermitian, performing H bar Hermitian divided by norm H times R bar. In the context of CDMA, this is precisely what is known as the rake receiver, that is performing this maximal ratio combining, combiner operation, or coherently combining these statistics R0, R1 up to RL minus 1. This process is known as rake reception, or this is known as the rake receiver in a CDMA system. This is known as the rake receiver in CDMA system, and therefore, the SNR at the output of the rake receiver, we have already seen the SNR at the output of the maximal ratio combiner. SNR at output of rake receiver equals, well, this is equal to norm h bar square P divided by the noise power is sigma square divided by n. So, this is precisely equal to n times norm h bar square times P divided by sigma square, which is equal to n times norm h bar square times the SNR, which is P divided by sigma square. Therefore, the output, therefore, the SNR at the output of the rake receiver is n times norm h bar square times P divided by sigma square, which is the SNR, which is the transmit SNR that we consider. And this n, as we know, is the spreading gain that is associated with the CDMA system. This is something that we already seen, this factor of n, this is the spreading gain this is the spreading gain of the CDMA system. This can also be you can also look at this norm, this is also equal to n times norm h square. I can write it as magnitude h0 square plus magnitude h1 square plus magnitude hl minus 1 square times the SNR. And you can also see this is basically the diversity combining across the L branches, and this is what leads to your multipath. This is diversity combining, and this is a new form of diversity in a CDMA. This is known as multipath diversity in the CDMA system. That is, this norm h square, which is magnitude h naught square plus magnitude h1 square, so on until magnitude hl minus 1 square, which is similar to that of a multiple antenna system, is what leads to the diversity in a CDMA or code division for multiple access system, and this is also termed as multipath diversity in the context of a CDMA system. And now you can also see that this expression is basically n times norm h bar square times SNR, which is n times, which if you can write this you can also write this as norm h bar square times n times SNR, which is basically replacing the SNR in a multiple antenna wireless system by n times SNR. Therefore, the bit error rate performance can be derived by substituting n times SNR in the expression we have for the multiple antenna wireless system. Therefore, the bit error rate, remember, at high SNR of an L antenna wireless communication system, bit error rate at high SNR is equal to 2L minus 1, choose L, times 1 over twice n times SNR raised to the power of L, but here where L is the number of frequency selective taps of the channel, and this n, this arises from the spreading gain of the CDMA system. This is the expression for the bit error rate, and of course, for this expression to hold, we must need that the channel taps H0, H1 up to HL minus 1 are IID, that is independent, identically distributed Rayleigh with average power 1. Okay, so for this, this is the bit error rate at high SNR when my channel taps, when the channel taps H0, H1 up to HL minus 1, when these are IID relay with average power, these are IID relay with average power is equal to 1. So, this is the expression for the bit error rate, that is 2L minus 1, choose L, 1 over twice n into SNR whole raised to the power of L. This is the expression for the bit error rate of a CDMA system with rake combining and with the channel taps distributed as IID relay random variables, IID relay channel coefficients of average power unity or average power 1, and you can see therefore, since the bit error rate is proportional to 1 over SNR raised to the power of L, the diversity order of this system is L, and this system therefore is able to extract multipath diversity. Therefore, this implies that, this also implies that diversity order is equal to L. Okay. So, to understand this better, let us do a simple example. To understand this better, let us do a simple example in this context of the CDMA. Consider an L equal to 3 tap, L equal to 3 tap frequency selective channel in a CDMA system. The code length n is equal to 256 and the SNR is equal to 15 dB, and the question we want to ask is what is the bit error rate of this CDMA system. That is, we are considering an L equal to 3 tap frequency selective channel, code length n is equal to 256, SNR is equal to 15 dB. What is the bit error rate? First, let us look at the SNR. The SNR in dB or 10 log 10 SNR is equal to 15, which implies my SNR is equal to 10 power 1.5, which is equal to, well, this is equal to 31.6228. Further, given the code length n is equal to 256. Also, we have the bit error rate is equal to 2L minus 1, choose L, 1 over 2 n SNR raised to the power of L. We have L is equal to 3, therefore, this is equal to 5, choose 3, 1 over twice into 256 into SNR raised to the power of 3, which is equal to 10 divided by 8 into 1 over 256 times SNR. The SNR is 10 to the power of 1.5. So, I have 10 to the power of 1.5 raised to the power of 3, and if you simplify this, you will get 2.36 into 10 to the power of minus 12. So, this is the bit error rate of the CDMA system in an L equal to 3 multipath channel with code length n equal to 256, which is 2.36 into 10 to the power of minus 12. So, what we have seen in this module is a new concept of multipath diversity in a CDMA system. We have seen how to model a frequency selective channel, how do we correlate with the various shifts of the code sequences at the receiver, how do we coherently combine them using the maximal ratio combiner, or basically what is also known as the rake receiver in a CDMA system, how this is able to extract the multipath diversity in the CDMA system, and also the associated bit error rate performance of the CDMA system with this rake reception. We were able to derive the expression for that and do a simple example to illustrate it. We will end this module here. Thank you very much.